Hi, it's time for another math easy solution. Today we're going to discuss further into differential equations and look at part B of example 1 of the seasonal growth population growth model as part of the other models series for population growth. And if you recall from my earlier my last video, I went over part A, and I'll put a link to that in the description below, so make sure to watch that. So basically in that example I went over a seasonal growth model, and I'll read that again. A periodic function of this in a seasonal growth model, a periodic function of time is introduced to account for seasonal variations in the rate of growth. Such variations could, for example, be caused by seasonal changes in the availability of food. And then part A, it was stating find the solution of the seasonal growth model. dp over dt equals to kp cosine rt minus phi, that's Greek symbol phi, where the initial value is given p of 0 is equal to p0, and where kr and phi are positive constants. So in my last video I went over part A and I solved that differential equation to get this solution of this seasonal growth model, which is the solution to that differential equation, which is this right here. And now part B, it states, by graphing the solution for several values of k, r, and phi, explain how the values of k, r, and phi affect the solution. It also says, what can you say about the limit as t approaches infinity of p of t of this population equation? So let's look at part B. So part B, the first thing is to graph this. So what I did, I actually made a Excel sheet like this, and what I did was I had different cases here, case 1, 2, and 3. So then for each case, for this one I just said initial population p0 is just 1, just easier to graph. And then for one case I made, so basically what I did was I made r across the board equal to 2, and then for this phi I made the angle equal to pi over 2. Then I varied k, so as you can see k is varied from 0.5 to 1 to 1.5, and then I grabbed this is the equation. I plugged in each one. As you can see, I just put the giant equation inside. You can check it out for yourself, but basically that's a population for these parameters, and this one's about these parameters, and this p of 2 is on the second one, and the 3 is involving the third third column of parameters. So I did this for up to the time from 0 to 7, and graphing it out you get something that looks like this. So let's just go over here. Yeah, so here I've copied and pasted that case right here, or for just varying k, and also that graph. So first let's consider varying k while keeping the other terms constant, and what we get is over here this graph. So this first one is where k is equal to 0.5, that's over here. So we varied k, keeping the other ones constant at those values, and then in between here, this dashed line, this is k equals to 1, and then finally this dotted line is k equals to this is 1.5. Let's write that here. So this k equals to 1.5. So as you can see, basically what's happening is these are getting higher and higher, except the minimums are all the same. Minimums are all the same, and that's what I wrote down here. As k increases, the amplitude increases, but the minimum values stay the same. The amplitude is just defined as the vertical distance between top and bottom parts of between the top and bottom parts of a wave. So for example, in this case here, this amplitude of this one is all the way here. That's the amplitude. I'll call that A, or just AMP dot, just amplitude. And then for these ones you have a smaller one, it's from here to here, and then this one is from the center here to there. So that's what those are. I'll just erase it. Yeah, just to make it neater. And then the next part I did was I varied r while keeping the other terms constant. So I kept k as 1, 1, 1 across the board, and I just made r as 1, 2, and 4. And you can play around with this and just type 1, 2, and 4, and as you can see, this changes like that. You get something that looks like that. So let's go back here. Actually, yeah, this looks a bit different. I forgot to make these constants. Just put this 1, 1, and then the scale goes up all the way higher than the 4, but I already fixed that earlier. So what we get is this right here. So the first one, R is, this is R not K, R equals to 1. And then the second dashed line, R equals to 2. And then the last one, R equals to 3. So as you can see, what happens, you have a big giant wave when it's R is equal to 1. But then what happens here is these dashed lines, then it becomes, well, smaller waves. And then when you get R bigger, you get many smaller waves like that. So basically, as R increases, the amplitude and period decreases. In other words, so the amplitude, again, initially R is small, so the amplitude is giant, and then it gets smaller and smaller. And the period is just the horizontal distance of a single wave. So for example, this one, it's when it starts repeating itself, so then the period is over here. So, but then for the dashed line is from here to here, so it's bigger. And this one, it's from here all the way to wherever this goes to the right side, like that. All right. So, and also another thing, just write these down. So this angle right here, these are, this angle is just equal to pi over 2, like that. And that's just 1.71, where pi is again 3.14, etc. So that's about 1.5-ish. Okay, and now the last part was, let's vary phi while keeping the other terms constant. So here I went from, this is pi over 4, this is pi over 2, and this one I went to pi. And then these ones kept these constant at, I'll just circle this. Yeah, these ones are kept constant. The 1 is, that 1 is just the initial population, and then K is 1, and then R is 2. And then when we change this phi, and I'll write this black one, it says phi equals to pi over 4, and then you have pi over 2 is equal to, over here, phi is pi over 2, and then the last one, this is pi over, or phi is equal to pi. So what happens here is you can see a change in phi produces slight adjustments in the phase shift and amplitude. So the amplitude, as you can see, it's a bit different here than this one, and also this one. So it doesn't necessarily increase or decrease it. It could do either or. Because as you can see, going from pi over 4 to pi over 2, it gets a bigger amplitude, and then what happens here, when you get it to pi is equal to, phi is equal to pi, which is the biggest angle, and this one, and that's a smaller amplitude than both of them. Yeah, I'm pretty sure than both of them. So there's slight adjustments, but again, they're pretty similar. And also in the phase shift is when a wave shifts or is displaced horizontally. So for example, from here to here, difference in phase shift is from the top here. So there's a displacement, or compared to this one, you have from here, yeah, all the way to here. This is a phase shift in there. So basically it gets shifted, and also amplitude changes when you're changing phi, and you could play around with that here. Just type 1, 1. Actually, no, this should be 2, 2, 2, and this one is pi over 4. Pi over 2, and this one is pi. So you get this graph like that. So anyways, and you can also put a link to that that Excel file to download for you to download if you want to play around with it. It's pretty interesting. Yeah, so now let's move further and look at the second part of part B, which is, what can you say about the limit as t approaches infinity of p of t? So let's write that down. Limit as t approaches infinity of p of t is equal to, this is going to be equal to limit as t approaches infinity of, now let's just plug that giant formula inside, which is this one here. P of t is equal to p naught or p0 e k over r, and sine rt minus phi plus sine r. So let's see if I memorize that correctly. This is going to be p0 and then e to the k over r times it by sine rt minus phi plus sine phi, like that. So yeah, that's correct. And now what this limit, the only thing that's varying with time is this rt, or the sine rt, so we could put that inside. So this just equals to p naught k over r, and then this is going to be limit as t approaches infinity of sine rt minus phi, and then plus this sine phi. So these ones aren't changing based on the t, only this value is. So what we have here is basically limit as t approaches infinity of this sine rt minus phi. This is basically approaching, well, t as it goes to infinity, this negative phi doesn't do anything because this is infinitely large and r is not going to change it. So this is approaching, well, sine infinity. So let's see what happens, what sine infinity. So recall, if you look at the sine function, so x, y, recall you had this goes up and down and up and down. Just a bad curve right there. Let's draw this a bit neater. It goes like that, up and down, up and down. I'll draw this one a bit neater too, where at this point here, this is pi over 2. That's the highest point. And then at, well, here, this is negative pi over 2. And this is a value of -1, and then this value is highest 1. So as you can see, it keeps going on and on forever. So as you go to x approaches infinity, it's just between 1 and -1 is the y value. So when we put that into this one, yeah, so what we have is that this sine infinity, well, as it's approaching infinity, what you have is it's alternating or oscillating between, it's just going up and down between -1 to 1. That's right, 2. So these values like that. So you don't actually get a value. So, yeah, so what we have is thus p of t oscillates, just going up and down between, now when you plug those values in, between p0 e krt, and now this is when this value is -1. When you plug in this sine rt minus phi is -1 to 1, you have, this is going to be, well, let's put a 1 there. So we'll just, so from, let's write -1 plus sine phi, so between this to phi 0, I mean p0 krt 1 plus sine phi, like that. Yeah, since it's alternating or oscillating between these, thus there is no limit. Thus, limit as t approaches infinity of p of t does not exist. Write that down and circle it like that. And yeah, so another note I want to go over before I end this video is basically a note: the extreme values of p of t are obtained when, and I'll explain that in a bit. Basically, because this is oscillating from -1 to 1, to find these are when basically sine rt minus phi are equal to plus or minus 1. So these are the extreme values here. Since this function is e to the power of this, you're subtracting 1, which is the largest negative number in sine rt minus phi. So that's an extreme on the low end, and this is plus 1 is the extreme on the upper end. So basically when these are equal to plus or minus 1, or when you look at how the sine function looks like, recall this one. So the extremes, you have this negative pi over 2, and then goes to pi over 2, and now from here to here separated by 2 pi, or which equals to 4 pi over 2. So when you add 4 pi over 2, let's write this better. So when you add 4 pi over 2 to negative pi over 2, that's just going to be, well, subtract 1. So that's going to be 3 pi over 2. And then from here to here is also separated by pi over 2. That's the period of it. So pi over 2 plus 4 pi over 2. This is going to be, well, 5 pi over 2. And going to the left side here, you can shift this one by negative 4 pi over 2. This is going to be negative 3 pi over 2. And this one you could just move by a pi, or so you can move by a negative pi, which is the same thing as negative 2 pi over 2 over to here, and this is going to be negative 5 over 2. Similarly here, this is negative 7 pi over 2, and then this part here we're just shifting again by pi, or 2 pi over 2. This is 7 pi over 2. So as you can see, the extreme values are whenever you have this as an odd number 1, odd number negative 3, odd number negative 5, odd number 5. These are all odd numbers in front of pi over 2. In other words, so basically the extreme values of the population function are obtained when sine rt minus phi is equal to plus or minus 1, or rt minus phi is equal to, and I'll write this as a times pi over 2, where basically a is equal to plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 7, etc. And again, these are all odd numbers, or odd integers. So right here, negative 5, negative 7, negative 3, negative 1, these are the extreme values, the top and bottom, or in other words, where a is equal to an odd number, or actually better than that, or I'll put this in bracket, or where rt minus phi is an odd multiple of pi over 2. So let's put that in bracket like that. Yeah, so anyways, I just wanted to go over that. Note, pretty interesting stuff. Anyways, that's all for today. Hope you'll learn from this pretty interesting video on seasonal growth and how trigonometric functions are used in seasonal growth models for population growth, just because they go pretty much up and down. So sometimes you have high growth, sometimes you have low growth, which trigonometric functions are great for modeling. Anyways, all for today. If you learn, like always, you can download these exact notes as well as the Excel file in the links below. So anyways, thanks for watching, and stay tuned for another Math Easy solution.